This video, we're going to talk about the IMF forces and how it deviates from the ideal gas laws. So the big question is, how are real and ideal gas laws different? So when we're talking about real gases have two scenarios. First, they behave ideally or they can behave in real settings. And so there are two conditions I want you to know about real gases when they do not behave ideally. And why is that important? Well, because if you know when the gas is not behaving ideally, you can definitely adjust and compensate for that given certain conditions. So number one is when they're under high pressure or when pressure is greater than 5 atmospheric pressure. Normal atmosphere is about 1 atm, and also at low temperatures, or it could be either or. So when things are really, really cold or when things are extremely high. And under such conditions, your PV equals nRT will not make accurate predictions. And so we've always been taught that in an ideal gas situation, certain conditions must be met. So if you're talking about the relationships between pressure and volume and looking at moles, you really want to make sure that you're under that 5 and definitely over at low temperatures. Now here's an example of a PV-nRT versus a pressure for 1 mole of an ideal gas. So if I take a look at ideal gas, this would be N equals 1 mole. So if I do the ratio of PV over RT and I give you 1 mole of that, that's how it should look like. However, if we go ahead and change it a little bit and it's below 5 atm, you definitely get a change if you're increasing the pressure. So for example, your CH4 begins to deviate as you're beginning to increase. So the number of moles of CH4 that you're getting when you're increasing that pressure changes. Same thing with your carbon dioxide and same thing with your helium. So anything below that 5 atm, which would be approximately this point right here, would be behaving as your ideal gas. Now, if you take a look at carbon dioxide as an example, the moment I begin to increase the pressure to about a 100 atm, you begin to see that the N value drops and slowly begins to increase, but then over time it deviates away from that ideal gas line. Now, volume adjustments need to be made for gases under high pressure. So the ideal gas law assumes that molecules do not have their own volumes. And so if you're taking a look at V in that, the V in PV equals nRT is the volume of empty space in the container. So remember that a couple of things you have to really think about, that many people think that it's the volume of the gas, but in reality it's the volume of the container. The volume of the gas particles are negligible, so when compared to the overall volume of the container, and this is due to the fact that the gas particles are very far apart and very small. So again, if I ask you what's the volume of a gas, what we're really talking about is that volume of the container because the particles are tiny. However, at high pressures, the molecules are compressed into much smaller volumes and the volume occupied by the molecules become more significant. So if I ask you why is it that at higher pressures the ideal gas law doesn't really take hold anymore, is because the moment you begin to pressurize that gas, you're squeezing those particles together, which now you can actually take that into account. Here's an example of something for gases under high pressure. So the volume occupied by the particles is negligible. So in this piece here on the left hand side, you can see if I take O2 as an example, they actually don't really occupy much space. In fact, majority of the space here is actually from the container. But if I increase the pressure or reduce that volume down, now you're beginning to see that the volume occupied by the particles is way more significant. And so because of that, you have to take into account what they call the NB value, or have to adjust for what they call the correction. So your volume is measuring the volume of the space plus the volume of the gas container, but the volume would only work during the lab. For the ideal gas, the corrected volume can be used. In this case, it would actually be the measure of the actual empty container. So N equals to the moles of the gas, and B is a constant for that type. So again, the more particles you have, the more likely you're going to get that. Now let's talk about the force of attraction in real gases. So the ideal gas law assumes that there are no forces of attraction between gas particles, but if the force is proportional to 1 over d6, then you begin to know that as you're getting closer and closer to these distances, your distance would actually increase your force. And this makes perfect sense because as you can see from this diameter, there is going to be a force that's going to increase as you're reducing that distance. Okay, so when we're talking about pressure adjustment for gases under high pressure or called low volume, gas particles become very close together, and because of that pressure, they're going to exert the forces that they exert may be less than what the equation would predict. Also, the neighboring molecules exert forces of attraction on one another when they're very close together. So again, kind of going back on this idea of like Coulomb's law type of analysis. And that force is going to pull the gas molecules in the direction opposites to its motion. This will in turn reduce the pressure resulting from impacts with the walls of the container. So again, I mean, the reason why we're talking about ideal gas laws and how they deviate from normal situations is we have to take into account these really small, tiny indicators that would show you that the volume would definitely change. Now here's another example of pressure adjustments. When you have a low pressure system, there is no force of attraction reducing impact velocity. So obviously the particle can move around, it doesn't really hit the wall, but if you're in a high pressured system, the forces of attraction will definitely reduce that impact because now it's going to be attracted to other gas particles, and that's going to affect the actual wall here. So you actually may get more attraction, more bouncing, and because of that, you have to adjust for that pressure. So when we're talking about pressure adjustments for gases under high pressures, or example, low volumes, we have to take into account this idea of the N2A V2, or the pressure to measure to ideal. So you have to consider the fact that when you measure pressure versus the ideal, you have to be able to expect what that ideal equation would be. And that would indicate how many moles you have, the constant for that gas, and also the volume. So we don't really have to know exactly how to calculate this, but take into account that it will show up at some point. All right, kind of putting it all together with van der Waals equation, if you really want to know the math about how to adjust for this, you basically combine your N2A V2 numbers and your NB for the volume. So again, you're dealing with pressure, you're dealing with volume, and you're going to be dealing with the nRT. In this specific case, what you're really looking at is the number of moles that's getting affected along with these constants. So here's an example of also the PVRT and how it changes depending on the temperature. So if I increase the temperature of any substance, you can kind of see that if we keep the temperature at going to be an ideal, it's going to be changing once the moment I begin to increase that temperature. So let's assume that your temperature increases, the behavior of that gas approaches that of an ideal. So this is going to be opposite of what we normally get when we're increasing, let's just say, pressure. So if you increase the temperature of the gas, you can kind of see that by about 300, we begin to get that approaching that situation where ideal is going to be our reference point. Now, the reason why gases do not behave ideally at low temperatures is because the gas experiences no intermolecular force of attraction. So things get really cold and the particles don't have that attraction. At high temperatures, the kinetic energy of the gas particles overcome any intermolecular forces, so they move around a lot. But at low temperatures, the gas particles move slower and are closer together, and because of that, those attractions between those molecules exist under those conditions. So moving back to condensation as an example. In condensation, the intermolecular forces of attraction increase as the distance between the particle decreases. And so if you take a look at these particles as they're slowing down, you begin to get more attraction. And this could lead to a condensation at significantly low temperatures or exceptionally high pressures. So this applies to all gases, even those with small forces. And so condensation can rapidly occur when the temperature of a system drops. So the kinetic energy of the gas particles is reduced and they move closer together. Under these conditions, the intermolecular forces can cause the particles to stick together when they collide. So I want you guys to think of it as more as like kind of like glue. When these attractions are occurring and they're getting really close, they begin to kind of stick. And this also occurs at high pressures, but it experiences a higher rate of collisions. So you kind of have to take into account the idea of kinetic energy, but you also have to take into account this idea of temperature. So again, kind of going back to this idea of interactions between gas particles. So when a system is approaching the point where condensation will occur, the forces of attraction between gas particles are at the maximum. And that kind of makes sense, right? So if we take a look at this picture, you can kind of see that these gas particles are all touching each other. As they get touch each other, they get a lot stickier. And this usually means that they're going to decrease the pressure and thus a larger deviation from ideal gas. All right, so in a summary, what did we learn from this? We learned a couple of things, that ideal gases usually can be violated in different scenarios where you cannot use the PV nRT formula if the following conditions are held. One is a low temperature, or two is going to be a high pressure system. And so if you kind of go all the way back to the ideal situation, you can kind of see that the more ideal it becomes, it has to follow these two conditions. And this has to do with the force of attraction between the gas particles and also the average kinetic energy, which begins to violate this idea that these gas particles are not going to have ideal gas behavior.